Two identical eigenvalues, one big question. Can this matrix be diagonalized? Watch as Gram-Schmidt saves the day and reveals the fascinating role of degeneracy in linear algebra. In our problem today, problem A29, we're told to consider the following Hermitian matrix, T as a 3 by 3 defined here. In part A, we're told to calculate the determinant and the trace of this matrix. In part B, we're told to find the eigenvalues of T and check that their sum and product are consistent with part A in the sense of equation A93. Write down the diagonalized version of T. So that'll be fun. And then in C, find the eigenvectors of T within the degenerate sector. Construct two linearly independent eigenvectors. It is this setup that is always possible for Hermitian matrices, but not for any arbitrary matrix. Contrast with problem A19. Orthogonalize them and check that both are orthogonal to the third. Normalize all three eigenvectors. In part D, construct a unitary matrix S that diagonalizes T and show explicitly that the similarity transform using T reduces T to the appropriate diagonal form. So last question we had the case for non-degenerate eigenvalues. This time we have the case for degenerate eigenvalues. So to start this problem, we just have to calculate a determinant pretty quick. Note that we're 3 by 3 Hermitian, so we can just expand about whatever row. There's no zeros, so we can just pick the first row. Here we get our normal setup. Go ahead and expand that with the subdeterminants crisscross across the board. We see we had a lot of negative signs canceling out, so be aware of that. With their I squareds coming back again, they turn to -1 pretty fast, so be again aware of those complex numbers. Negative, negative cancel. Then we see our result of brackets, 2 times 3, 3i squared plus minus 3. Simplify that out. We see we get 6 minus 3 gives us this 3 here. 3 and -1 give us this -3 here. So our resulting determinant is 0. That's kind of nice, but also we'll have to verify that. And then our trace, thankfully, is easy enough. We just sum across the main diagonal terms, and that gives us 2, 2, 2, so add them together gives us 6. Now let's see if these are verified with the eigenvalues. So to get the eigenvalues, once again, we use the characteristic equation. So set up our determinant, lambda on the main diagonals, all equal to 0. First row again, since we already had that form set up. Now we can see that crisscross on the subdeterminants or the minors. Go ahead and we see bracket, bracket, bracket for the subdeterminant evaluations. Go ahead and be careful with the algebra because that is the crux of it all. Form the characteristic polynomial here. We see that every single every single term has a lambda in it, so we'll factor that out with the minus sign. Turns this into a factorable quadratic where we just have lambda minus 3 squared. So since we have all three terms here, we know that our three eigenvalues are 0, 3, and 3. Note that 2 and 3, lambda 2, lambda 3 repeat for the same values, so we are degenerate. As such, we need to verify the determinant and trace properties from A93, where the determinant was the product of the eigenvalues, so 0 times anything is going to be 0. Cool. Trace is the sum of the eigenvector or eigenvalues, so 0, 3, 3 gives us 6 again, so we are good and confirm that. Now, getting back to the messy part of all these questions, the eigenvectors. Again, to determine the eigenvectors, we substitute each of the distinct eigenvalues into the characteristic equation. Upon doing so, we see that 0 doesn't shift the matrix at all, so we're left with this homogeneous system of linear equations, and once again we'll solve it with Gaussian elimination. Here's our row ops, get that first entry down to 1, and then we'll go ahead and multiply constants to each row and simplify down, get a 0 here. Couple more row ops, get the 0 here, Now we can add these two rows together with the multiple of I as we see indicated here. And then we see we get a 0 row in the bottom, so we know that row is redundant. From there, we can go ahead and simplify our second row, and then finally cancel out this element here in the first row. So this gives us a solution set where we have one free parameter, namely that we solved A1 for A3 and A2 for A3, which leads us to the general solution of A1, A2, A3, where we substitute in our linear equation substitutions. And we see that A3 again is our free parameter, so we'll set that equal to -1 to get these negatives out front, and we see we get our eigenvector as such. Not too bad. Now the next one is going to be a little more difficult because that is the degenerate eigenvalue. So set up our characteristic equation again. We see now we have -1 on the main diagonal versus 2, and we still have 3 components here, so setting that equal to 0. Again, a homogeneous linear system of equations. Go ahead and solve it down. As you see, we only needed 3 row ops this time. But here we have to be careful because we have 1 row of zeros, 2 rows of zeros. So this tells us that we had a redundancy in 2 rows. This means that when we do our substitution, or when we break this down into equation form, B1 is an equation based on 2 free parameters, B2 and B3. Okay, and this should make sense because of the fact that we have the degeneracy in the eigenvalue. So when we put this into general form, B1, 2, 3, substitute in B1, we can linearly make or separate these into their constituent parts for free parameter B2 and B3. And the presence of these 2 free parameters is justified by the degeneracy or multiplicity of the eigenvalue. This degeneracy necessitates the assignment of the convenient values for these free parameters. As such, we get to choose them. Consequently, we want to choose, in this case, let B2 equal -I and B3 equal 0. As we see, that gets rid of the second column here completely. And this -I puts a 1 right here, so that's what we like to do. Then for our second free parameter substitution, we want B2 to equal 0, so that gets rid of that column, and then B3 equal 1, since we're good to go, and that gives us our second eigenvector from the eigenvalue 3. So makes sense, we just needed to make 2 free parameter adjustments on it for the degeneracy. But now, of course, being a quantum mechanics book, we have to go ahead and normalize these. So V1, 1, 1, just take the conjugate transpose, dot product it out, hence the negative on the I there from the conjugate transpose. And then we see that we just get 1, 1, 1, so root 3, not too bad. Similarly for V2 right here, we get a root 2 because of that 0. And then lastly, we'll also have a root 2 because of this 0 here. So ultimately, this is what our landscape is looking like. Now, there is going to be a problem here because of the degeneracy that happens between V2 and V3 and that they're related to the same eigenvalue. When we are related to the same eigenvalue, that does not necessarily mean that we're orthogonal because of the association. So we're going to have to make that happen. So we need to first verify orthogonality. So orthogonality states that there is no overlap between any of the vectors, right? If we are orthogonal, they're sitting at 90 degrees to one another. So the inner product or dot product should go to 0. Here with the normalization factors in our bracket, we see that we end up after plugging these in and calculating 1, -1, and 0. That gives a 0. So V1 and V2 are orthogonal. What about V1 and V3? Well, yeah, that's orthogonal too because of 1 minus 0 after simplification. But the problem happens with the 2 vectors that come in from the same eigenvalue. We see we get 1 and 1, then a 0 and a 0. So 1, 0, 0. We end up with a 1/2 overall, which is not 0, so they're not orthogonal. Now, as a result, these last 2 vectors not being orthogonal, this tells us that we need to employ the Gram-Schmidt orthogonalization process and subtract off whatever the projection was from V2 onto V3, right? And then get rid of that so that we can have an orthonormal basis. So if we recall, I can't remember what vid, I think it was A4 when we did Gram-Schmidt. But what we see is that for the new vector, we take the current vector minus the projection or overlap, and then on the second vector and just minus that off, okay? So here, normalization, the overlap or dot product, which is given here, and then our old vector. Now we see that we have 1 over root 2 in both of these terms, but we have a 1/2 here. So instead of leaving this 1/2 here, we'll factor it all out. And note that this was 1, 0, 0, or 1, 0, 1. So in factoring out this 1/2 from both terms, we had to put in a 2. So this purple vector goes to 2, 0, 2. From there, we can just subtract them off element-wise. So 2 minus 1, 0 minus negative I, which goes to 0 plus I, and 2 minus 0, leaving us with a 1, I, 2. Now, it's important to recall that we have to renormalize this after the fact. So in the renormalization, we get a 1 over 2 square root 2 times square root of 6. But the 1 over 2 root 2 cancels out with this one up here. So we're good to go. So now we just need to go ahead and re-verify that these are indeed orthogonal. Now note that V1 and V2 are orthogonal, so we don't need to check that. What we do need to check is V1 and V3. Okay, we see that once again since V3 got what's the word I'm looking for? Got redefined rather. We see that we just have to plug in the new values, so 1, I, and 2. We get 1 plus 1 minus 2 after simplification. That's 0, so we're good. And then for V2, V3, the original problem child, we see that 1, 1 plus I, and then 0, 2. We see that we're left with 1 minus 1 plus 0, so we do indeed get the orthogonality that we look for. We just had to shave off the projection on it, and thus we're left with a new orthonormal bases for lambda 1, 2, and 3 and their associated eigenvectors. Now, this is important because we needed these in order to go ahead and try to diagonalize. If the vectors don't span the space, then we can't diagonalize the matrix. So that's why we had to do this. So knowing that diagonalization is coming up next, let's go ahead and fix ourselves in an algebraically advantageous position. And go ahead and we see that we have a root 6 here, the lowest common denominator, so to speak. We can force a root 6 into this green 3 and green 2 by multiplying by quote 1, where the 1 is 2 over 2. And then from there, we see that this 3 and this 2 create that 6. We're dividing by root 2 here, so dividing by a fraction, multiply by the reciprocal. Once we multiply by the reciprocal, we put it into every component. Thanks to the vector space axioms, we can go ahead and do that. Same argument here, just 2, you need to multiply by 3 over 3 instead of 2 over 2. And then we see that we get this here. Now that this is all cleaned up, we can get straight to diagonalization and verify. So we have to also remember here the rules of diagonalization. And the fundamental criterion for matrix diagonalizability is the existence of a complete set of linearly independent eigenvectors equal in number to the matrices dimensionality. Given that the condition is satisfied now thanks to Gram-Schmidt, we can proceed with the diagonalization process. And the construction of the matrix S inverse, or P in the linear algebra books, is achieved by arranging the eigenvectors of T as column vectors. So S inverse, or if you're using linear algebra books, that's denoted as P. We have V1, V2, V3 prime, all as the eigenvectors for the columns. And we see that we get the 3 by 3 matrix here. That is to be used in the similarity transform. Now, we know from the question itself and from other proofs that this matrix S inverse has to be a unitary matrix. As such, we can take the dagger of both sides, or the conjugate transpose, and that is the inverse of the inverse. so we can get our S matrix. As such, dagger up here, we're good to go. Normalization doesn't matter, so green column goes to green rows, column to row, column to row. Everything that had a complex part on it, we have to switch the signs, as we see indicated in yellow. And now we can go ahead and diagonalize the matrix T from this similarity transform. As we see here, it's defined as ST S inverse, so we have both S matrices and we know what T is. Let's go ahead and plug it in. As such, we have normalization here for S, as we see color coded down, T, our original matrix, the normalization factor, S as we see here from up top, or S inverse from up top. Now let's just multiply these out and see what we get. So normalization is now taken out front, getting rid of the curly brackets. We see that this matrix multiplied to this matrix. Component-wise, again, very tedious, so be careful with the work. We see that that gives us a column of zeros and a row of zeros, so that should help us a lot with the next steps. And then we have this little submatrix in here, this block of 3, 3, 3, 3 values, so that'll come through again. We note that we have a 1/6 out here because of the normalization. Root 6 times root 6 gives us 6, so we're good to go. And now we take this matrix, multiply it into this one, leaving us with something surprisingly simple, a 0, 18, and 18 on the main diagonal. As it should be, it's a diagonalized matrix. But are they equal to the eigenvalues? And indeed they are, because once we distribute the 6 to every element, they simplify down to 0, 3, 3, which are the eigenvalues. So we are indeed good to go and have thus diagonalized this matrix for degenerate eigenvalues. Very fascinating and very important. Oh, wow. Okay, so this series is quickly coming to a close, but this has been a lot of fun. So definitely be on the lookout for what's coming next. The journey will keep going, and all we're doing is building these building blocks one day at a time. That being said, got to run quick today, so thank you for everybody for your patience and enjoying the process with me. It's definitely been helpful, especially all the feedback going into New Year's. I think this will be viewed in February, so definitely look forward to hearing all the feedback on this as time progresses. So thank you, thank you, thank you. And as always, thank you for watching. Until next time, stay curious.